Welcome to EC Elimu Learning Simplified and welcome to this lesson. In the previous lesson, we discussed the principle of moment. Now in this case, we are going to discuss moments of parallel forces, where we are going to realize that when you have parallel forces acting on either side of the pivot, then the sum of upward forces is going to be equal to the sum of downward forces, or in short, the algebraic sum of forces or of moments in a system in equilibrium is zero. By the end of this lesson, I expect you to be able to describe moments of parallel forces, and then later you will do some questions concerning moments on parallel forces. So parallel forces, these are forces that can never meet. It means they form 90 degrees to this common line here, which is in contact or which is in line with the pivot. So it means every force here is 90 degrees to this point. Therefore, it means they are parallel and they can never meet. So if they happen to be in a system which is in equilibrium, equilibrium means it is the system, it has a state of balance at the pivot. Therefore, we're going to realize that for this one to be at equilibrium, it means the forces which are acting on one side, that is upwards, must be equal to the forces which are acting downwards. At the same time, the clockwise moments must be equal to the anti-clockwise moment. Now, let's look at the forces which are acting here. Force F3 and F1 are acting on the left-hand side. One is acting upwards, the other one, F3, is acting downwards. Then we have force 2, which is acting on the right-hand side upwards. We have force 4 acting on the right hand downwards. Then force 5, which is acting on the right hand downwards. Then now F3, this one which we have here on the left hand side, is causing anti-clockwise moment. Anti-clockwise moment, because if it pulls this rule downwards, it's going to make it to rotate in anti-clockwise direction. F1, if it moves up, it's going to cause clockwise moment because it makes this rule to rotate in a clockwise direction like that. This one causes it to rotate like that. Then F2, if you pull it upwards, it will cause anti-clockwise moments, anti-clockwise moments. Then F3, F4, and F5, this clockwise moment, and also this one is a clockwise moment. It's very important for you to note that. However, as much as these forces F1, 2, 3, 4, 5 are acting on this rule like that, we also have another force which is acting on this rule. In this case, this force is caused by the reaction force by this pivot. Remember what we discussed in Form 1? Types of forces. We said we have a force which we call action and reaction force. Whenever a body is resting on another body, the body is acting action, and then the body itself, the one in which the other one is resting on, is exerting reaction. So we also have a reaction force, but its direction is upwards. So in this case, on the upward forces, we have three of them: F1, F2, and reaction force. And then downward forces, we have F3, F4, and F5. So in this case, if I can highlight forces upwards, the forces which are acting upwards are F1, then we have reaction, then we have F2. Then forces acting downwards, forces down, we have F3, we have F4, and we have F5. So according to the law which governs the parallel forces, it states that for a system which is in equilibrium, the sum of forces on one side, it should be equal to the sum of the forces which is acting on the other side. Or in simple terms, the algebraic sum of forces is zero. This means forces upwards should be equals to the forces acting downwards. In this case, we can write in this case in terms of, since we have forces upwards and forces downwards, F1 plus reaction plus F2 should be equal to F3 plus F4 plus F5. That is, the algebraic sum of the forces is 0. That's what we mean. Then the sum of the forces upwards is equal to the sum of the forces downwards. And this idea is very important in this part or in this topic and in physics in general. Another thing that you should note is that for a system of parallel forces, the sum of clockwise moments is always equal to the sum of anticlockwise moment. And in this case, the algebraic sum of moments, we can summarize it as the algebraic sum of moments of parallel forces is 0. Clockwise moment should be equal to anticlockwise moment for this system to be in equilibrium. So we can handle a few questions concerning parallel forces. And in this case, the first question reads, figure shows a system in equilibrium. It means it has clockwise moments equal to anti-clockwise moments, or sum of upward forces equals to sum of downward forces. Then we have AB. This is this bar from here to the other end. AB is a uniform ruler or rule of length 1 meter. So from here to this end, it's 1 meter. So it means this 100 centimeter is 0 centimeter. Then of negligible weight. So this rule does not have any weight. Calculate weight W. They want us to calculate this weight here, W. Then 2, find the tension on this spring T. In this case, they want us to find a reaction force, or the force upwards. So in this case, for us to find force W, then we are going to use the principle of moment, which says sum of clockwise moments is equal to the sum of anti-clockwise moments. In this case, we want to know which force can cause clockwise moment. In this case, W, if you pull it down, is going to cause anti-clockwise moment. Then for the one with 80, if you pull it down, it's going to cause clockwise moment. So if you know that, then in this case, let's call this one F1, and then the distance from the pivot, this is the pivot here, P, then the distance from the pivot is going to be, if this is 100 and this is 40, then it means here it is at a mark of 60 on this rule. Then if this is 60 and this is 20, it means this distance here for F1, which you can call D1, is 60 minus 20, which is going to be 40 centimeter. So that is D1. Then we can call the other side D2. This 40 is equals to D2. And then this force 80 is F2. So now the clockwise moment that we have here is caused by this force F2. So here clockwise moment is F2 times D2 is equals to anti-clockwise moment, which is caused by F1. That is F1 times D1. Now, do we have F2? Yes, we have it as 80. So since we have F2 as 80 Newton, which is causing clockwise, times the distance from the pivot, which is 40 centimeter. If you want to make it in meter, you divide by 100. Then it's going to be the same as anti-clockwise moment. Anti-clockwise moment, we have W as our F1, which we don't have. That's what we're looking for, times D1. In this case, we have 40 over 100, this case meter. So if you are keen enough, you will realize that this side of 40 over 100 will cancel out with this 40 over 100. Then we will remain with our W is equals to 80 Newton. So the force that we need as W should be 80 Newtons. But if we don't cancel like that, let's handle it fully. So in this case, it would have formed, let's say this one is sealed out. That's how you can cancel it like that, but that's not, we can do it another way. So in this case, if we do it 80 Newton times 40 divided by 100, that is 0.4 meter, is equals to W times 40 divided by 100 is 0.4 meter in this case. So in this, if we want W, we divide by 0.4 meter, divide by 0.4 meter. Then in this case, 0.4 meter on the right hand side will go. Then on the left hand side, 0.4 meter will cancel with 0.4 meter. So here it will be 1, 1. So in this case, we will remain with our W as 80 Newton. So you can do it either way. If you are quick enough, you can cancel out 40 over 100 because they appear equal on both sides, or you can go the long way and you will still get the same answer. Then the second question they are asking, find the tension on the string, tension on the string TP. Remember what we said, the sum of forces on one side should be equal to the sum of forces on the other side for a system to be in equilibrium. So if we should handle that second part on this small box here, it's enough. So the tension B2, then in this case we will say sum of upward force is equals to the sum of downward force. In this case, do we have upward force? The only upward force we have is T, that is tension. Then it should be equal to the sum of downward force. Sum of downward force, we have 80 as W and the other 8 on the other side. So it is 80 plus 80, which is tension. In this case, it's going to be 160 Newton. So for you to get now the sum of upward force, you add the sum of downward forces, then it will give you the sum of upward forces. Then the second question, the figure below shows a meter rule balanced by 4 forces at its center. Then we have a meter rule, we have force W1, let's call it F1, this is our F1. Then we have F2, which is 100, F3 and F4 as our 30. Then at W, which is F1, we have a distance of 5 meters from 0. Then we have 30, it's at 50, the pivot is at 50, 80, we have 150, 90, we have 30 Newton, and then we have 100 as the bar of that meter rule or a metal bar. Then in this case, they are asking the question, determine the weight W. We want to determine this weight W, which is the same as F1. For us to determine this, then we need to calculate, to use the principle of moment, which says the sum of clockwise moment is equals to the sum of anti-clockwise moments. In this case, let's first find out what force is causing what moment. If you pull this W down, what will it make this rule to turn? It will turn in an anti-clockwise direction, so it will give it anti-clockwise moment. So also the force which is 100 F2, if you pull it down, it's going to cause anti-clockwise moment. Then F3, if you pull it down, it's going to cause clockwise moment. It's going to make this rule to turn in a clockwise direction. Then F4 is also going to cause clockwise moment. Then now the principle says the sum of clockwise moment is equal to the sum of anti-clockwise moment. Then in this case, for us to get a moment, if we know that we have a force, then we need a distance from the pivot. In the first case here, F1, the distance from the pivot is this one here, from 5 to 50. It means this is 45 centimeter. This is D1. Then F2, we have this distance from the pivot. 50 minus 30 is 20 centimeter. This is our D2. Then D3, this force F3 to the pivot. In this case, it's 80 minus 50, which is 30 centimeter. Then finally, D4 is 90 to 50, which is 40 centimeter. This is our D4. Now, if we have force and distance, then we can calculate moment. In this case, clockwise moment, this is the first clockwise moment here, this one here. Then this is the second clockwise moment. So clockwise moment is caused by forces F3 and F4. So if we can write them here, the clockwise moment will be F3 times D3 plus F4 times D4. That is the sum of clockwise moments, which will be equals to the anti-clockwise moment. There are two caused by F1 and F2. That is, anti-clockwise moment now will be F1 D1 plus F2 D2. And therefore, in this case, these are sum of anti-clockwise moment. Now, if we substitute the F1, F2, D, whatever in this equation, then the sum of clockwise moment will be 150 Newton as F3 times D3, which is the same as 30 centimeter, which is 30 over 100 in meters now. Then plus, this case, we want to add total sum of clockwise moment plus another F4. F4 in this case is 30 newtons times D4, which is 40 over 100 centimeter for it to be in meter. So in this case, what we have got here is the clockwise moment. These are clockwise moments. Then we can calculate anti-clockwise moments, sum of anti-clockwise moments. If we calculate sum of anti-clockwise moment here, we are going to use F1 times D1. F1 is what we are looking for, W, times D1, which is 45 over 100 meter, plus F2 D2, that is 100 Newton, times D2 is 20 over 100 centimeter for it to be meter. So in this case, this is the total anti-clockwise moment. Then now, if we solve the first one, that is clockwise moments, then they are going to be 150 times 0.3, 150 times 0.3, which is going to give us 45 plus 30 times 0.4, 30 times 0.4. This case is going to give us 12. So these are the clockwise moments. Is equals to sum of anti-clockwise moments. We have 45 over 100, which is the same as 0.45 W. That's what we are looking for. Then meter W plus 100 times 0.2, 100 times 0.2, which is the same as 0 or 20, which is the same as 20 Newton meter. So in this case, as you can see, we have on this left hand side, if we can sum it up, it will be 45 plus 12, which is going to be 57 Newton meter is equals to 0.45 W plus 20 Newton meter. We have common units here, Newton meter. It means these are like terms. Then we can bring this to this side here. If we bring it on this side, it will become a negative, and then we will have 0.45 meter W is equals to 57 minus 20. It's going to be 37 Newton meter. And then now, if you need W, will divide by 0.45 meter, divide by 0.45 meter, not 0.0, 0.45 meter. Then in this case, 0.45 meter will go like that. This case meter will cancel with that meter. Then we will remain with 45, or not 45, but 37 divided by 0.45, which is going to give us 82. So in this case, the W, which is the same as F1, is 82.22 Newton. That is the force that we need to exert as our W. Then in this case, they are asking what is the reaction at the pivot. Remember, reaction at the pivot is acting upwards. Reaction here will be acting upwards, and that will be the only upward force. And we said we can do it here. This space is enough. We said upward forces, sum of upward force, up force is equals to down force. Then in this case, since these forces are parallel, we can use this principle. Then here, for us to get sum of upward force, which is reaction is equals to be the sum of downward forces. That is 82.22 plus 100 plus we have 150 plus 30 Newton. This case, if you add 82.22 plus 100 plus 150 plus 30, it's going to give you the reaction in this case here, R is equals to 362.2 newtons. That is the sum of forces upwards which are experienced as a reaction force. So that marks the end of our lesson today. In the next lesson, we will discuss more examples on the principle of moment and parallel forces.